Tonight, everything familiar begins to shrink. The Earth, the Sun, the Solar System, even the Milky Way. Step by step, the universe reveals a truth that is far colder than fiction. Humanity does not merely live in something vast. Humanity exists as almost nothing inside it. In this video, the scale keeps pulling farther back until every human measure of size begins to collapse. If this kind of deep space journey belongs on the channel, please like the video, subscribe, and stay with the channel for more quiet explorations into the darkest truths of the cosmos. The chilling truth about our size in the universe begins now. At the largest scale that observation can reach, the universe appears as a pattern of light stretched across immense darkness. It does not spread its galaxies evenly in all directions like grains scattered by a steady hand. Instead, matter gathers into long strands, broad walls, dense knots, and vast openings where far fewer galaxies shine. This arrangement is known as the cosmic web. A web in this sense is not a solid object and not a woven surface. It is a name for the large pattern formed by matter under gravity across the observable universe. The observable universe is the part from which light has had time to arrive since cosmic expansion begins. Beyond that limit, space may continue, perhaps far beyond all present measurement, but observation remains bounded by light and time. From this widest view, the first impression is not fullness but separation. The dark regions between bright structures are enormous. These spaces are called voids. A void is not perfectly empty. A few galaxies may still drift there, and thin matter may still remain. But compared with richer regions, the void holds very little. Around these low-density spaces, galaxies collect along filaments that can extend for hundreds of millions of light-years. A light-year is the distance light travels in 1 year. The term measures distance, not time. Along the filaments, gravity has drawn matter into forms that become the grand scaffolding of the visible cosmos. This pattern does not appear immediately after the universe begins. In its earliest known state, matter and radiation are far more uniform, though not exactly smooth. Tiny differences in density exist. Some regions contain slightly more matter than others. Over immense spans of time, gravity strengthens these small differences. Places with a little extra matter pull in more matter. Places with a little less become emptier by comparison. The result is the slow growth of structure. The web emerges not from design, but from physical law acting over deep time. It remains one of the clearest signs that the universe changes, evolves, and develops form from simple beginnings. Dark matter plays a central role in this large arrangement. Dark matter is matter detected through gravity rather than light. It does not appear to emit, absorb, or reflect light in the ordinary way, yet its gravitational pull helps shape galaxies and larger structures. Observations indicate that most of the matter in the universe is dark matter, not the ordinary matter found in stars, planets, gas, dust, and living things. In the broadest maps of the cosmos, ordinary matter follows the deeper gravitational framework made largely by dark matter. The visible web of galaxies therefore traces a larger invisible web beneath it. What dark matter is made of remains uncertain, but its large-scale effect is strongly supported by many lines of evidence. The scale of this structure presses against ordinary language. A single galaxy is already enormous, containing millions to trillions of stars. Yet on the largest maps, even galaxies become points, and whole clusters of galaxies resemble beads along faint strands. A human life unfolds on a surface of one small planet around one ordinary star in one galaxy, among many billions within the observable universe. From the level of the cosmic web, the familiar world disappears completely. Not only cities and mountains, but stars and even individual galaxies lose their usual importance. Size becomes relational. What seems immense at one scale becomes negligible at another. The observable universe itself extends for tens of billions of light-years in every direction from Earth when described in terms of present-day distance. This does not place Earth at a true center. Every distant observer in a similar galaxy would also see space expanding away and would trace an observable region around their own position. The apparent centrality comes from the nature of observation, not from a special place in the cosmos. Space expands, carrying galaxies apart on large scales. Because of that expansion, the most distant light reaching modern instruments comes from matter that is now much farther away than the simple travel time of light alone might suggest. Even this largest visible region is not a complete picture of all that exists. Observations define a horizon, and the horizon defines an edge to knowledge, not necessarily an edge to reality. Beyond the observable limit, no present telescope can see. Cosmology, the study of the universe as a whole, can infer some conditions from models and measured patterns, but direct observation remains incomplete. The total universe may be vastly larger than the observable part. It may even be spatially infinite. At present, observations indicate that the large-scale geometry of space is very close to flat, but whether the whole universe is finite or infinite remains uncertain. Within the observable region, the web appears in surveys that chart galaxy positions across deep space. These maps reveal that structure repeats at great scale without becoming simple. Filaments intersect. Dense regions grow where strands meet. Voids open between them. The pattern has no obvious preferred direction. It does not arrange itself around human expectations of symmetry or closeness. Instead, it reflects the history of expansion, gravity, and matter over billions of years. The eye may try to find comfort in shape, but the actual lesson is distance. Most places are unimaginably far from one another. Most matter lies far from stars like the Sun. Most of the universe is not made of environments suited to life as known on Earth. Light from remote galaxies also carries another quiet truth. To look far outward is to look backward in time. Because light travels at a finite speed, distant objects appear as they were when that light begins its journey. The most remote observable structures are seen in youth, not maturity. Nearer galaxies appear in a more recent states. The outermost observable region is therefore also the oldest visible layer of cosmic history. Distance and time overlap. The widest setting is not only spatially remote, it is temporally ancient. From this far perspective, human measures of large and small begin to lose stability. The planet that seems vast to its inhabitants vanishes below detection. The Sun becomes one star among many. The Milky Way becomes one galaxy within a strand. The strand becomes one feature in a web crossing an observable universe so large that light itself requires billions of years to move between its major structures. The chilling fact is not violence or hostility, it is proportion. The known human world occupies no meaningful share of cosmic size. It rests within layers of structure so extensive that ordinary intuition cannot hold them all at once. At the outermost visible scale, existence appears as a thin dusting of luminous matter, tracing a hidden framework across a darkness that extends farther than any direct sight can reach. Where the long filaments of the cosmic web meet, matter gathers more tightly. These junctions hold some of the most massive assembled structures that gravity keeps together. They are galaxy clusters. A galaxy cluster is a collection of galaxies bound by their shared gravity, along with large amounts of hot gas and a much greater mass of dark matter. A smaller gathering is often called a group. The distinction is not always sharp, but a cluster is larger, richer, and more massive. Some contain a few hundred galaxies, some contain 1,000 or more. Between those galaxies lies a space that appears dark to the eye, yet it is filled with thin gas heated to such high temperatures that it shines in X-rays rather than visible light. At this scale, the universe looks less like scattered islands and more like weathered terrain. Dense regions stand out like high ground. Clusters mark those high points. They sit within the deepest wells of gravity on large scales, drawing in matter from their surroundings over billions of years. Galaxies fall toward them. Gas flows inward. Smaller groups merge into larger systems. The cluster grows slowly, not as a single event, but as a long accumulation. Its shape is often uneven because growth continues. Some clusters appear rounded and settled. Others show signs of recent mergers, with substructure still visible in their galaxy distribution and in the hot gas spread between them. The hot gas inside a cluster is called the intracluster medium. The term simply means the gas within the cluster. It is extremely thin by everyday standards, far thinner than any laboratory vacuum on Earth would appear at first thought. Yet because it fills such vast volumes, its total mass is enormous. In many clusters, this gas outweighs all the stars in all the member galaxies combined. It reaches temperatures of millions of degrees, heated by gravitational collapse and violent motions as matter falls inward. At those temperatures, atoms lose electrons and the gas becomes plasma, a state of matter made of charged particles. This plasma glows in X-rays, allowing space observatories to trace where the cluster's ordinary matter lies. The galaxies are the most familiar parts, but they are not the main mass. Dark matter dominates the cluster overall. This becomes clear when astronomers compare different ways of measuring a cluster. The speed of galaxies moving inside it gives one estimate of total mass. The temperature and spread of the hot gas gives another. Gravitational lensing gives a third. A gravitational lens is a bending of light caused by mass. When a very massive cluster lies between Earth and more distant galaxies, the cluster's gravity bends the passing light and distorts the background shapes. By measuring those distortions, astronomers map the mass that must be present, including dark matter. These different methods agree on the same broad conclusion. The visible stars form only a small fraction of the whole. The gas contributes more. The largest share is invisible except through gravity. Within a cluster, galaxies do not sit in peace. They move rapidly, often at speeds of many hundreds or more than 1,000 kilometers per second. The distances between them are still great, so direct collisions between stars remain rare, but entire galaxies can interact, distort one another, or merge, especially in smaller groups that later become part of a cluster. The cluster environment also affects the gas inside galaxies. As a galaxy travels through the hot intracluster medium, pressure can strip away some of its own gas. Without that gas, star formation may slow or stop. Over time, many cluster galaxies become dominated by older stars. In this way, a cluster is not only a gathering place, it is also an environment that changes the histories of the galaxies inside it. At the center of a rich cluster, there is often a very large galaxy, brighter and more massive than most of its neighbours. This central giant likely grows through repeated mergers and by drawing in matter over long spans of time. Around it, the cluster extends across millions of light years. A nearby example is the Coma cluster, a well-studied system containing many thousands of galaxies across a region more than 20 million light-years wide. It is not exceptional in principle, only in clarity and usefulness to observation. Many other clusters lie farther away, and some are seen in earlier stages of formation. Observations show that massive clusters already exist when the universe is much younger, though the earliest phases of cluster formation remain an active area of study. Beyond the level of a single cluster lies a looser arrangement often called a supercluster. The name suggests an even larger version of the same kind of object, but the reality is subtler. A supercluster is a broad association of clusters, groups, and galaxies spread across a huge region. Unlike a rich cluster, a supercluster is usually not one single gravitationally bound object. Its parts influence one another and share a common large-scale environment, yet the whole structure may not remain intact forever. Cosmic expansion continues to pull widely separated regions apart. For this reason, superclusters are better understood as major features of the cosmic web rather than as single settled systems. They mark where matter is especially concentrated over very large distances. The Milky Way belongs to a small group of galaxies called the Local Group. This group lies near the outer region of a much larger supercluster environment known as Laniakea. The name refers to a vast region mapped partly through the motions of galaxies as they flow under gravity. Such mappings help reveal that the universe has structure above the scale of clusters, but they also show the limits of simple categories. There is no clean wall around a supercluster in the way there is no clean shoreline in fog. Density rises and falls gradually. Filaments connect one concentration to another. Boundaries depend partly on how the structure is defined. Seen from this region of scale, the human sense of size shifts again. A galaxy that seemed like a complete world in itself becomes one member of a crowded assembly. Even a cluster, enormous by any ordinary standard, is only one knot within a broader pattern. The striking fact is not merely that these structures are large, it is that they reveal how much of cosmic form is collective. Galaxies rarely stand entirely alone. They gather, move, merge, and respond to shared gravity in systems far beyond the scale of any single star or planet. In the densest regions of the web, the universe builds not isolated lights, but communities of galaxies held in dark matter and hot plasma, suspended across spaces so large that even these communities remain small compared with the full cosmic field around them. Below the scale of clusters and loose supercluster regions, the galaxy becomes the next clear unit of structure. A galaxy is a vast system of stars, gas, dust, and dark matter held together by gravity. It is not a simple collection of scattered suns. It has form, motion, internal weather, long memory, and a history written in light. At this scale, matter that seemed nearly abstract in the cosmic web becomes visible as recognizable systems with shapes that can be mapped and compared. A galaxy may contain a few million stars at the small end or several trillion at the large end. Between these limits lies a great range of sizes, masses, and structures. The Milky Way belongs to the larger class, though it is not among the most massive galaxies known. The oldest broad distinction between galaxies is their shape. Some are spiral galaxies, with flat rotating disks, central bulges, and sweeping arms marked by gas, dust, and young stars. Some are elliptical galaxies, smoother in appearance, with stars moving in many directions rather than chiefly in ordered rotation. Others are irregular galaxies, lacking a clean, simple form, often because they are small, disturbed, or shaped by recent interactions. These categories describe appearance, but appearance reflects deeper physical differences. A spiral galaxy usually contains abundant gas and ongoing star formation in its disk. An elliptical galaxy usually contains older stars and much less cold gas. An irregular galaxy may still form stars actively, though its structure appears patchy or asymmetrical. A spiral galaxy presents one of the clearest examples of order emerging from motion. Its disk rotates around the center, but not like a solid wheel. Inner regions orbit more quickly than outer ones. The spiral arms are not fixed rails of stars that remain in place forever. They are better understood as patterns of higher density moving through the disk, somewhat like crowded regions in traffic. Gas enters these denser regions, becomes compressed, and can form new stars. Bright young stars then light the arms, making them stand out in visible light. This helps explain why spiral arms appear vivid and structured, even though the stars themselves continue moving through the pattern over time. An elliptical galaxy tells a quieter story in appearance, though not always in origin. It may look smooth and settled, with little dust and few sharp features, but many ellipticals are thought to arise through mergers between smaller galaxies. In such events, the organized disks can be disrupted. Stellar orbits become scrambled into a more rounded system. Gas may be consumed in bursts of star formation or heated and expelled, leaving an older population behind. The result is often a galaxy dominated by long-lived, cooler stars. These stars tend to shine with yellower or redder light than the hot blue stars found in vigorous star-forming regions. The colour of a galaxy therefore offers a broad clue to the age of its visible stellar population, though dust and composition also affect the picture. Irregular galaxies occupy a different place in this landscape. Some are small and have never built a stable disk or bulge. Others are disrupted by nearby companions or by past interactions. The Large Magellanic Cloud and Small Magellanic Cloud near the Milky Way are examples of nearby irregular dwarf galaxies. A dwarf galaxy is simply a small galaxy, but small does not mean unimportant. Dwarf galaxies are numerous and play a major role in models of galaxy formation. Large galaxies likely grow in part through the accumulation and merger of smaller ones. Streams of stars around some big galaxies appear to be remnants of dwarfs, pulled apart by tidal forces, meaning differences in gravity from one side of the smaller system to the other. At the center of most large galaxies lies a supermassive black hole. A black hole is a region where gravity is so strong that once matter passes a certain boundary, called the event horizon, it cannot escape. A supermassive black hole can contain millions or billions of times the mass of the Sun. Observations strongly indicate that such objects occupy the cores of many galaxies, including the Milky Way. The black hole does not usually control the whole galaxy in a direct mechanical sense, because the galaxy is vastly larger than the black hole's immediate region of strong influence. Yet the growth of the central black hole and the growth of the galaxy appear linked in important ways. In some galaxies, matter falling toward the black hole releases enormous energy, creating an active galactic nucleus that can outshine the rest of the galaxy. In others, the black hole is comparatively quiet. Gas and dust within galaxies are as important as stars for understanding galactic life. Gas provides the raw material for new stars. Dust, though only a small fraction of the mass, shapes how light moves through the galaxy. Dust grains absorb and scatter blue light more effectively than red light, making some regions appear dimmer and redder. Dense clouds of cold gas and dust can collapse under gravity to form stars, especially when disturbed by spiral density waves, shock fronts, or collisions between clouds. As new stars form, the most massive among them live briefly and die violently, enriching surrounding gas with heavier elements. In astronomy, elements heavier than hydrogen and helium are often grouped under the term metals. These heavier elements become part of later generations of stars, planets, and dust grains. This means a galaxy changes chemically as well as structurally. Early in cosmic history, galaxies contain mostly hydrogen and helium, the lightest elements. Over time, stars create heavier elements in their interiors and return part of that material to surrounding space through winds and explosions. Later stars therefore form from gas that has already been enriched. This long recycling process helps determine what kinds of planets may eventually form and what materials become available. A galaxy is therefore not merely a container of stars. It is a system that processes matter over billions of years. Dark matter surrounds and extends beyond the visible body of a galaxy in a halo. A halo in this sense is a broad, roughly spherical region around the galaxy. The evidence appears in rotation curves, which track orbital speeds at different distances from the center. If only visible matter were present, orbital speed in the outer parts would usually decline more strongly with distance. Instead, in many galaxies, the speed stays higher than expected. This indicates additional unseen mass. The stars, gas, and dust that can be photographed are only the bright inner trace of a larger gravitational structure. At the scale of the galaxy, the universe becomes more intimate than the scale of clusters, yet the sense of human smallness deepens rather than fades. A galaxy contains distances so vast that light requires tens of thousands to hundreds of thousands of years across it. Stars are separated by expanses that make planetary systems vanish into insignificance. The forms of galaxies seem serene when viewed from afar, but that calm appearance conceals ceaseless motion, star birth, stellar death, black holes, magnetic fields, radiation, and the slow working of gravity across dark matter halos. The galaxy stands as a middle kingdom of the cosmos, far below the grand web yet far above the scale of any world where life might look up and imagine it. The Milky Way is the galaxy that holds the sun, the planets, the surrounding gas and dust, and the thin band of light seen across a dark sky from Earth. At this scale, the universe is no longer an abstract population of galaxies. It becomes one specific structure with known broad dimensions, known components, and a known place for the solar system within it. The Milky Way is a barred spiral galaxy. This means it has a flat rotating disk with spiral arms, and at its center it contains an elongated bar of stars rather than a simple round bulge alone. The galaxy is about 100,000 light-years across in its main stellar disk, though its wider halo extends much farther. It contains a few 100 billion stars, along with gas, dust, star clusters, and a dark matter halo that reaches well beyond the bright parts. From within the Milky Way, no outside view is available in direct observation. The galaxy must be reconstructed from many measurements taken from inside the disk itself. Dust blocks visible light along many lines of sight, especially toward the crowded central regions. Radio waves, infrared light, and precise measurements of stellar motions help reveal the structure that ordinary sight alone cannot show. The broad result is clear. Most of the galaxy's stars lie in a flattened disk. In that disk, stars, gas, and dust follow spiral structure. At the centre sits a dense bulge and bar. Around the whole system lies a much larger halo, sparse in stars but important in mass and history. The galactic disk is the Milky Way's most familiar body because it contains the spiral arms and most of the stars visible in the night sky. It is broad compared with its thickness. If reduced in imagination to the scale of a large plate, it would be far wider than it is deep. Within this disk, stars orbit the galactic centre over immense periods. The Sun takes roughly 200 million years to complete one orbit. A single circuit of the galaxy is therefore longer than the time since the first dinosaurs appear on Earth and vanish. Galactic motion is steady, not hurried. Even at speeds of hundreds of kilometers per second, the distances are so large that one orbit becomes a span beyond ordinary biological history. The spiral arms are regions where stars, gas, and dust are more concentrated. They are not rigid structures. They are patterns within the rotating disk, made visible in part because gas clouds there form young luminous stars. These young stars are bright and short-lived, so they mark recent star formation and make the arm stand out. The Milky Way appears to have several named arm features, though the exact mapping of all branches and spurs is not perfectly simple. Two major arms emerge clearly from the ends of the central bar, and other arm segments and smaller structures extend through the disk. The solar system lies not in one of the grandest central arms, but in a smaller feature called the local arm, also known as the Orion arm or Orion spur. This places the Sun in a modest position between larger spiral structures, neither at the centre nor at the farthest outer edge. The central bulge and bar form the dense inner heart of the Milky Way. The bulge contains many older stars packed more closely than in the disk. The bar is an elongated concentration crossing the centre and influencing the motion of stars and gas in the inner galaxy. At the very core lies Sagittarius A star, the compact radio source associated with the Milky Way's central supermassive black hole. Its mass is about 4 million times that of the Sun. Although this sounds dominant, the black hole is tiny compared with the galaxy as a whole. Its importance is greatest in the inner region, far away in the disk where the Sun moves. The combined gravity of stars, gas, and dark matter shapes the orbit far more directly than the black hole alone. Beyond the disk and bulge lies the stellar halo, a broad, roughly spherical region containing relatively few stars compared with the disk, but extending to great distances. The halo includes many globular clusters, which are dense, ancient swarms of stars. These clusters are among the oldest known parts of the galaxy. Their stars preserve evidence of earlier stages in galactic history. The halo also contains streams of stars, which are the remnants of smaller systems stretched apart by gravity as the Milky Way grows over time. This provides strong support for the view that the galaxy is not a finished object formed all at once. It develops gradually, partly through the capture and merging of smaller galaxies. The dark matter halo extends farther still. It cannot be seen directly, but its presence is inferred from orbital motions and other gravitational evidence. The visible galaxy sits within this much larger invisible structure. In one sense, the bright Milky Way is only the inner luminous trace of a broader gravitational domain. This enlarges the true size of the galaxy beyond what the eye would guess from starlight alone. It also means that the solar system moves not just inside a disk of stars, but inside an enormous halo of unseen matter. The Sun is located about 26,000 to 28,000 light-years from the galactic centre, roughly 2/3 of the way from the centre to the visible outer edge of the disk. This is a stable and informative distance. Closer to the centre, stars are packed more densely and the environment is more intense in radiation and gravitational disturbance. Much farther outward, heavy elements become less abundant on average, and the density of stars decreases. The Sun's position lies in a region that is neither central nor remote. It is ordinary by galactic standards. The ordinary nature of this location is part of the larger pattern. Again and again, the human setting appears not at a centre, not at an edge of privilege, but in a middle zone of a larger system, seen as a whole. The Milky Way is serene only at a glance. Inside it, stars are born in cold clouds, live for millions or billions of years, and die in ways that return matter to space. Gas flows through the disk. Dust dims and reddens starlight. Magnetic fields thread the interstellar medium. Star clusters form and disperse. Smaller galaxies pass nearby or are slowly absorbed. The disk pulls. The halo preserves old debris. The center hosts a black hole. All of this occurs within a structure so large that even light needs 100,000 years to cross its visible breadth. At the scale of the Milky Way, the idea of home becomes more precise and more unsettling. The Earth is not merely in a galaxy. It is in one outer region of one spiral arm feature, inside one rotating disk around one center, that lies far beyond any direct human travel. The familiar night sky is not a ceiling, but an internal view from deep inside a vast stellar system. Human life unfolds in a narrow corner of that system, on a planet too small to alter the galaxy and too slight to appear in any map of it. The Milky Way is already so large that the whole history of civilization occupies no measurable fraction of one galactic orbit. Between the stars of the Milky Way lies a region that seems empty at first glance. It is not empty. It contains gas, dust, magnetic fields, radiation, and fast-moving particles, all spread through a volume so large that even very thin material becomes important. This region is called the interstellar medium. The term simply means the matter and energy between stars. At the scale of a planetary surface, a gas this thin would appear almost absent. At the scale of a galaxy, it becomes one of the main ingredients from which future stars and planetary systems arise. It is the medium through which starlight travels, through which shock waves move, and within which the Milky Way slowly renews itself. Most of the interstellar medium is gas. Much of that gas is hydrogen, the lightest and most abundant element in the universe. Helium comes next, with smaller amounts of heavier elements mixed in. The gas does not exist in one single uniform form. It occupies several broad states that differ in temperature, density, and motion. Some regions are cold and relatively dense, though still extremely thin by Earth standards. Some are warmer and more diffuse. Some are so hot that atoms are stripped of electrons and the gas becomes plasma. These states can exist side by side across the galaxy, shaped by gravity, radiation, magnetic fields, and the explosive deaths of stars. Cold interstellar clouds hold special importance because they are the places where matter can gather most effectively. In the densest parts of these clouds, hydrogen often exists as molecules rather than single atoms. A molecule is a small group of atoms bound together. Molecular hydrogen is difficult to observe directly in many conditions, so astronomers often trace these clouds through other molecules, especially carbon monoxide, and through the glow or shadow of dust. Molecular clouds can span tens to hundreds of light years. Some contain enough mass to form many thousands of stars. Within them, dense knots and filaments develop. Gravity can then pull parts of this material inward until new stars begin to form. In this way, the quiet, dark cloud becomes one of the most active nurseries in the galaxy. Not all interstellar gas is cold. Large volumes are warmer and more diffuse, filling wide regions between denser clouds. Ultraviolet light from hot young stars can strip electrons from nearby hydrogen, creating ionized regions around stellar nurseries. These regions glow in visible light and can appear pink or red in astronomical images because of the way excited hydrogen emits light. Other parts of the interstellar medium are heated by supernova explosions, the violent deaths of massive stars. These explosions drive shock waves through surrounding gas, compressing some regions and heating others to millions of degrees. The interstellar medium is therefore not static. It is stirred repeatedly by stellar birth and stellar death. Dust makes up only a small fraction of the interstellar medium by mass, but it has a strong effect on what the galaxy looks like. Dust grains are tiny solid particles made chiefly of heavier elements such as carbon, silicon, oxygen, magnesium, and iron, arranged in compounds or mixed structures. These grains form in the outflows of evolved stars and in stellar explosions, then pass into the interstellar medium where they can be altered, coated, broken, or incorporated into new clouds. Dust absorbs and scatters light, especially at shorter wavelengths. Because blue light is scattered more strongly than red light, distant stars seen through dust often appear dimmer and redder than they otherwise would. This effect helps astronomers estimate the amount of dust along a line of sight. But it also means the Milky Way hides part of itself from ordinary view. The dark lanes visible across the band of the Milky Way in a clear sky are examples of dust obscuration. They are not empty gaps in the stars. They are regions where dust blocks the visible light from more distant stars behind them. In infrared light, some of these hidden regions become easier to study because infrared light passes through dust more effectively than visible light. Radio astronomy reveals even more, tracing hydrogen gas and molecules through the galactic disk. Much of what is known about the Milky Way's structure comes from looking through these longer wavelengths, since direct optical sight is limited by the dust spread through interstellar space. Magnetic fields thread the interstellar medium as well. These fields are weak compared with the laboratory magnet on Earth, yet across interstellar distances they influence the motion of charged particles and help shape the structure of gas clouds. They can guide flows, resist compression in some directions, and affect how clouds collapse into stars. Their exact role in many cases is complex and still under study. But observations show that the interstellar medium is not governed by gravity and heat alone. It is also an electromagnetic environment, subtle but persistent. Cosmic rays move through this medium too. Cosmic rays are fast-charged particles, mostly protons and atomic nuclei, travelling at very high speeds. Many are likely accelerated in shock waves from supernova remnants, though not all sources are fully settled. As these particles pass through the interstellar medium, they contribute to ionization and energy transfer. They are another sign that the space between stars is active, not vacant. Even in darkness, events continue. Particles cross long distances, radiation spreads outward, clouds cool, collapse, or disperse. Matter cycles from one form to another. This cycling is one of the most important features of interstellar space. Stars form from interstellar gas and dust. During their lives, stars release light, winds, and particles back into that same medium. Near the end of their lives, many return enriched material to space, massive stars explode and send heavy elements outward. Lower mass stars shed outer layers more gently. The interstellar medium receives these materials, mixes them over time, and becomes the source of later generations of stars and planets. The calcium in bones, the oxygen in air, the silicon in rocks, and the iron in blood all trace back to earlier stars and to the interstellar recycling that spread stellar products through a galaxy. At human scale, the space between stars sounds like absence. At galactic scale, it is one of the main places where history is stored and the future is prepared. It is thin, cold in many regions, hot in others, dark in some directions and luminous in others, but never truly inert. The vast separation between stars does not mean there is nothing there. It means that what is there must be understood differently. Interstellar space is a sparse ocean of gas, dust, fields, and radiation, extended across distances so great that whole solar systems drift through it like almost invisible motes. The Milky Way is not made only of stars. It is also made of the dim material between them, and that dim material is where much of the galaxy's continuing life begins. Within the Milky Way's disk, the Sun exists among a small crowd of nearby stars that share a broadly similar galactic environment. This region is often called the local stellar neighborhood. It is not a walled district. It is a portion of the galactic disk defined by proximity and by practical observation. At this scale, the galaxy's spiral arms and distant center fade into background context. The focus becomes the spacing of stars, the kinds of stars that appear nearby, and the gentle structure of matter and motion that surrounds the Sun before any specific boundary of the solar system is considered. The nearest stars are still far away. The closest known stellar system, Alpha Centauri, lies a little more than 4 light-years from the Sun. This distance is so large that even the fastest spacecraft built so far would require many thousands of years to reach it. Such distances define the local environment. In a typical region of the Milky Way's disk like this one, stars are separated by several light-years on average. Space is therefore mostly empty between them, yet not empty in the absolute sense. The interstellar medium continues here as it does elsewhere, though the local conditions vary. The local neighborhood includes stars of many types. Most are smaller and cooler than the Sun. These are red dwarfs, low-mass stars that burn their fuel slowly and can live for tens to hundreds of billions of years. Many are faint and difficult to see without careful surveys, which means the nearby population of stars looks different through a telescope than it does to the naked eye. The bright stars visible in the night sky are often not typical. They are bright because they are either relatively close, intrinsically luminous, or both. The true majority nearby is dim and quiet. Alongside red dwarfs are stars more similar to the Sun, known as yellow dwarfs, though the term is informal. These are main sequence stars, meaning they fuse hydrogen in their cores. A main sequence star is one that spends most of its life in this stable phase. There are also hotter and more massive stars, but these are less common because they are short-lived. A massive star burns fuel quickly and lives only millions of years before ending its life in a supernova. The local region does not contain many such stars because no major star-forming region lies very near the Sun at present. The nearby bright stars include some that are larger and more luminous than the Sun, including giants that have evolved beyond their main sequence phase. These evolved stars help show that the local population includes different ages and stages of stellar life. The Sun's neighborhood is also shaped by the local interstellar medium in a particular way. The solar system lies inside a region of relatively low-density hot gas, often called the local bubble. This is a cavity in the interstellar medium extending for hundreds of light years in some directions, believed to have been carved by supernova explosions in the past. The gas inside is thin and hot, and the cavity is not perfectly spherical. It has uneven boundaries and openings into other low-density regions. Evidence comes from measurements of interstellar absorption lines, X-ray emission, and the distribution of nearby clouds. The exact history of how the local bubble forms, including how many supernovae contribute and when, is still studied. But the broad picture of a low-density cavity around the Sun is supported by multiple observations. Within or near this cavity lie small, denser clouds of interstellar gas and dust. The Sun appears to be moving through a local interstellar cloud, sometimes called the local interstellar cloud. This cloud is thin, but denser than the surrounding bubble. It contributes neutral atoms and dust grains that can drift into the outer regions influenced by the Sun. These details matter because they shape the boundary region where the Sun's outward flowing particles meet the interstellar medium, though the solar system itself remains for later focus. For the local neighborhood, what matters is that even here, between nearby stars, interstellar conditions shift from cavity to cloud and from warmer regions to colder ones. Stars in the neighborhood share motion in the galactic disk, but they do not move as a rigid group. Each star follows its own orbit around the Milky Way's center, and each has smaller motions relative to the local average. Over time, these motions mix stars from different birthplaces within the disk. The Sun itself likely forms within a cluster or association, and then drifts away as the group disperses, as many stellar nurseries do. Nearby stars today are therefore not necessarily siblings of the Sun. Some may form in similar regions of the galaxy, others may come from somewhat different radii or from different times. The local neighborhood is a momentary gathering defined by present positions, not by shared origin. The space between local stars contains more than gas and dust. It is filled with starlight, a background field of photons coming from many directions. It is also filled with infrared glow from dust warmed by radiation. Farther background radiation from the universe beyond the galaxy passes through as well. In addition, there are small bodies not bound to any star that may drift through the region, though such objects are difficult to detect. A few interstellar objects have been observed passing through the solar system in modern times, suggesting that wandering bodies between stars exist and can occasionally enter a star's vicinity. Their overall abundance remains uncertain because detection is difficult and depends on chance encounters and survey sensitivity. In this neighborhood, the Sun is not a standout star in terms of mass or brightness. It is a middle-sized main sequence star. Its significance comes from the planetary system that forms around it and the life that develops on one of its planets. Yet at this scale, that significance is not visible. The Sun is one among many, separated from its nearest stellar neighbors by distances that dwarf the size of the entire solar system by orders of magnitude. The planets would be lost even within the light of the Sun if seen from a few light years away. The nearest stars would still look like points. Even within the local neighborhood, size and distance impose a quiet hierarchy. Stars are immense compared with planets. Yet the voids between stars are larger still. The local stellar neighborhood therefore offers a steady and sobering measure of proportion. It shows that even within a single galaxy, the environment around one star is a vast volume where encounters are rare and where travel is constrained not only by engineering, but by the sheer scale of space. It also shows that the Sun's immediate setting is shaped by the broader galaxy through interstellar cavities, clouds, and long-lived motions. In this region, the universe is no longer the cosmic web and no longer the whole Milky Way. It is a sparse field of nearby suns moving through thin gas and faint dust, within a cavity carved by ancient explosions, under a background of steady starlight that carries information from countless distant sources, far beyond the known planets, far beyond the bright disk of the Kuiper Belt, and far beyond the region where sunlight still shapes familiar worlds in a direct and visible way. There is thought to be a vast surrounding shell of icy bodies. This is the Oort cloud. It has never been seen directly. No telescope has produced an image of it as a complete structure. Its existence is inferred from the orbits of long-period comets, and from dynamical models that explain how such comets can arrive from extremely distant regions in many different directions. In this sense, the Oort cloud is both one of the largest parts of the solar system and one of the least directly observed. It is known mainly through its effects. A long-period comet is a comet that takes more than 200 years to orbit the Sun, and many take far longer than that. Some return only after thousands or millions of years. Their paths are highly elongated, carrying them from deep outer darkness into the inner solar system and then back outward again. Their directions are not confined to the flat plane in which the major planets travel. Instead, they can arrive from almost any angle. This is one of the key clues behind the idea of the Oort cloud. If these comets came mainly from a flat disk alone, their orbits would tend to cluster around the planetary plane. The observed spread of orbital inclinations suggests a roughly spherical reservoir surrounding the Sun rather than a thin outer ring. The Oort cloud is understood as a remnant of early solar system history. In the youth of the Sun, the region of giant planet formation contains large numbers of icy bodies. Many are scattered outward by gravitational encounters with Jupiter, Saturn, Uranus, and Neptune. Some are ejected from the solar system entirely. Others are placed onto extremely distant elongated orbits. Over time, the weak but persistent gravity of passing stars and the broader tidal pull of the Milky Way alter these far orbits, raising them into a more spherical distribution. The result is not a structure built in place, but one assembled through scattering and long-term gravitational reshaping. The Oort cloud therefore records the solar system's early disorder as much as its later stability. Its scale is immense. The inner edge of the main Oort cloud is often estimated to begin at around 1,000 astronomical units from the Sun, though some models allow a denser inner region beginning farther in, or merging gradually with other distant populations. An astronomical unit is the average distance between Earth and the Sun. The outer edge may extend tens of thousands of astronomical units, perhaps approaching 100,000 astronomical units. At such distances, the pull of the Sun becomes weak compared with the more local dominance it has over the planets. The gravity of nearby stars and the galactic environment begin to matter more strongly. The Oort cloud lies near the frontier where the solar system stops being a sharply self-contained domain and becomes instead a loose gravitational territory shaped by its surroundings. Because of this, the cloud is not expected to be dense. It is not a close-packed swarm of icy bodies drifting side by side. It is more like a vast shell in which the average separation between objects may still be enormous, even if the total number of bodies is very large, perhaps in the billions or more. The volume they occupy is so great that emptiness remains the dominant condition. In ordinary imagination, a cloud suggests softness and nearness. In astronomy, the Oort cloud is almost the opposite. It is cold, sparse, dark, and extended across distances so large that one icy nucleus may be separated from the next by millions of kilometers or more. Most of its bodies would be small, dark, and almost impossible to detect directly from Earth. These icy bodies are thought to be primitive remnants from the early solar system, composed largely of frozen water, carbon dioxide, carbon monoxide, methane, ammonia, rock, and dust. Because they spend most of their existence far from the Sun, they preserve material that changes little for immense spans of time. When one is disturbed and begins to fall inward, sunlight heats it as it approaches the inner solar system. Ices turn directly into gas, dragging dust with them and forming the glowing coma and tail associated with comets. In this way, an object from the distant Oort cloud can briefly become one of the most visible bodies in the sky. Its brightness near the Sun is temporary, but its origin lies in darkness almost beyond the region usually imagined as the solar system. The forces that disturb Oort cloud bodies are gentle compared with planetary collisions, yet over long periods they are effective. A passing star does not need to come very close to Earth to influence a distant comet reservoir. At the scale of the Oort cloud, even a remote stellar passage can alter orbits. The steady tidal field of the Milky Way also changes them over time. A tidal force is a difference in gravity across distance. For a very distant object weakly bound to the Sun, these small differences accumulate. A body may be nudged inward, outward, or fully removed from the Sun's hold. Some comets that reach the inner solar system may therefore be messengers from ancient outer storage, released by processes unfolding across millions of years. The cloud may also have internal structure. Many models distinguish an outer Oort cloud, more spherical and weakly bound, from an inner Oort cloud, sometimes called the Hills cloud, which would be more tightly held by the Sun and may contain a large fraction of the total population. The outer region is more easily disturbed and more likely to send comets inward directly. The inner region may act as a deeper reservoir, feeding the outer region over time. Observations support the idea that the source population is not a single simple shell, but details of the inner distribution remain uncertain. Since the cloud cannot yet be imaged directly, its exact shape, total mass, and population size are inferred with wide margins rather than measured cleanly. This uncertainty is part of what makes the Oort cloud scientifically careful territory. Observations indicate that long-period comets exist, and that many arrive on orbits consistent with the distant spherical source. Models of solar system formation and dynamical evolution also support such a reservoir. Yet the total number of objects, the exact inner boundary, and the detailed distribution of masses and orbits remain uncertain. The Oort cloud is therefore accepted in broad outline, but not known in the same way as a planet or moon seen directly. It stands as a structure inferred from motion, pattern, and consequence. At this region of scale, the solar system becomes difficult to imagine as a family of planets circling in tidy order. The planets occupy only a tiny inner fraction of the Sun's wider gravitational reach. Beyond them lies a dark population spread into a sphere so large that the nearest star begins to feel conceptually less remote. The familiar worlds of the inner system are almost central sparks compared with this outer shell. Human history unfolds on one planet that circles the Sun once each year. An Oort cloud comet may take longer than all of recorded civilization to complete one orbit. Here the measure of smallness shifts again. Earth is not merely far from the edge of the universe, it is far from the edge of its own extended solar system. Inside the distant spherical reach inferred for the Oort cloud, the solar system becomes more structured again. The next major outer region is the Kuiper belt and the broader trans-Neptunian domain beyond Neptune. This is not a sphere but a flattened population of icy bodies orbiting mainly near the plane of the planets. It is broad, cold, and sparse, extending far beyond the orbit of Neptune while still remaining much closer to the Sun than the main body of the Oort cloud. Here the solar system retains a memory of its original disk-like form. Bodies move in long, slow paths through darkness where sunlight is weak. Temperatures are extremely low, and orbital periods stretch across decades, centuries, or much longer. The Kuiper belt begins just beyond Neptune, at about 30 astronomical units from the Sun, and extends to around 50 astronomical units, though its edges are not sharp in a simple physical sense. Beyond it lie additional populations of trans-Neptunian objects on more distant or unusual orbits, including the scattered disk. The term trans-Neptunian object simply means a body whose orbit lies mostly beyond Neptune. Some of these objects follow relatively circular paths. Others travel on highly elongated or tilted orbits, evidence of past gravitational scattering. Together they show that the outer solar system is not empty space between a last planet and an imagined end. It is a region populated by ancient icy remnants, shaped by the gravity of the giant planets and by the early migration of those planets through the young solar system. The bodies in this region are made largely of ices mixed with rock and organic compounds. In planetary science, ice includes not only frozen water but also substances such as methane, nitrogen, carbon monoxide, and carbon dioxide that are solid at these low temperatures. These objects preserve material from the early solar system more directly than the inner, rocky planets do. Closer to the Sun, heat and repeated geological processing alter surfaces and interiors more strongly. In the Kuiper belt, many bodies remain deep frozen and chemically primitive, though they are not unchanged in every respect. Radiation, impacts, and seasonal effects on some larger objects still modify their surfaces over time. The Kuiper belt is sometimes compared with the asteroid belt, but the comparison must be handled carefully. Both are populations of smaller bodies left over from solar system formation, yet the Kuiper belt is much larger in extent and richer in ice. The asteroid belt lies between Mars and Jupiter and is dominated by rocky and metallic bodies. The Kuiper belt lies far beyond Neptune and is dominated by frozen materials. Its objects are also generally spaced very far apart. In drawings, they often appear packed densely for convenience, but the real belt is mostly empty. A spacecraft passing through it is not likely to find crowded debris. The dominant experience would still be isolation. Within this region are dwarf planets, bodies large enough for their own gravity to pull them into a nearly round shape, but not large enough to clear other comparable objects from their orbital neighborhoods. Pluto is the most famous example. Once classified as the 9th planet, Pluto is now understood as one of the largest known members of the Kuiper belt. Its orbit is elongated and inclined compared with the 8 major planets, and it shares the outer solar system with many related bodies. This does not make Pluto less real or less interesting. It places Pluto in a truer context. It is not an isolated final planet, but part of a much broader population that reveals the solar system's outer architecture. Pluto itself is a complex world. Observations from the New Horizons mission show mountains of water ice, plains of frozen nitrogen, layered atmospheric hazes, and signs of active surface renewal. Its moon Charon is large relative to Pluto, making the pair an unusual binary-like system in dynamical terms. Other large trans-Neptunian objects include Eris, Haumea, and Makemake. Eris is slightly smaller than Pluto in diameter, but more massive. Haumea has an elongated shape and a rapid rotation. Makemake shows a bright icy surface. These bodies differ from one another in composition, reflectivity, moons, and dynamical history. The outer solar system is therefore not uniform. Even in darkness and cold, diversity appears. Neptune's gravity plays a major role in shaping the Kuiper belt. Some objects are in resonances with Neptune, meaning their orbital periods relate to Neptune's in simple ratios. Pluto, for example, is in a 3:2 resonance, completing 2 orbits around the Sun for every 3 of Neptune. This resonance protects Pluto from close encounters with Neptune despite their crossing paths in projection. Resonant populations show that the outer solar system preserves a record of migration. Many models indicate that the giant planets do not form exactly where they are now. Instead, they shift position in the early solar system, scattering smaller bodies and trapping some into resonances as they move. The current pattern of the Kuiper belt supports this broader picture, though details of the timing and exact paths of migration remain subjects of active research. Beyond the main Kuiper belt lies the scattered disk, a population of icy bodies on more elongated and often more tilted orbits, likely shaped by stronger past interactions with Neptune. Some of these bodies travel hundreds of astronomical units from the Sun at their farthest points. Sedna, with its extremely distant and elongated orbit, occupies an even stranger category, often described as part of the detached population because Neptune alone does not seem sufficient to explain its path. Objects like Sedna suggest that the solar system's outer reaches retain signatures of events that are not fully settled. Possible influences include early stellar encounters, unseen past dynamical effects, or the broader birth environment of the Sun within a stellar cluster. Observations indicate the outer system is more complex than a single simple belt, though not all causes are known with confidence. Sunlight in this region is weak, but it is not absent. At Pluto's distance, the Sun still shines far brighter than the full moon shines on Earth. Yet compared with Earth daylight, it is extremely dim. Shadows are still cast, horizons still exist, ice still reflects light. A large body here is not in total darkness by day, but in a distant muted daylight under a small intense sun. The thermal environment is severe, and orbital seasons can last for decades or centuries depending on the object. Surface frosts can shift. Thin atmospheres may freeze and collapse, then partly return when sunlight increases. Slow change defines the region. At the scale of the Kuiper belt, the solar system's inner worlds have already become remote. Earth is just one small inner planet, invisible to the naked eye from most of these distances. The giant planets no longer dominate the sky unless one is near Neptune. The Sun remains central, but its warmth has largely failed to reach this far in any familiar way. The human homeworld lies deep inside, close to the furnace of the star. Out here, the solar system appears as a vast cold plain of ancient remnants and scattered dwarf worlds, moving with patient slowness around a sun that has already dwindled into a bright point. The unsettling truth continues to sharpen. Even after passing beyond the planets, the solar system is still not close to its end. Within the cold outer domain beyond the Kuiper belt's main body, the giant planets stand as the largest settled worlds of the solar system. Jupiter, Saturn, Uranus, and Neptune dominate this region in mass, in size, in gravitational reach, and in the number of moons and rings that accompany them. They are not simply bigger versions of Earth. They belong to a different class of planetary body, made mostly not of solid rock and metal at the surface, but of deep layers of gas, fluid, and high-pressure matter surrounding smaller inner cores or core-like regions. Jupiter and Saturn are usually called gas giants because hydrogen and helium make up most of their bulk. Uranus and Neptune are called ice giants because they contain proportionally more water, ammonia, methane, and other heavier materials beneath their atmospheres. All four are large enough to reshape nearby space. Jupiter is the largest planet in the solar system by far. Its mass exceeds the combined mass of all the other planets together. It orbits the Sun at about 5 astronomical units, which places it beyond the asteroid belt and well inside the colder outer system. From a distance, Jupiter appears as bands of cloud wrapped around a rotating globe. These bands mark high winds, changing storms, and differences in chemistry and temperature. The most famous feature is the Great Red Spot, a vast, long-lived storm larger than Earth. Jupiter has no solid surface in the familiar sense. Its visible top is an atmosphere of hydrogen and helium with cloud layers of ammonia, ammonium compounds, and water deeper down. Beneath the clouds, pressure rises until gas behaves as fluid, and farther inward, hydrogen enters unusual states under immense compression. Jupiter's gravity gives it enormous influence. It shapes the asteroid belt through resonances, captures Trojan asteroids that share its orbit, perturbs comets, and helps determine which bodies remain in stable paths and which are scattered inward or outward. The planet acts as both a protector and a disturber. Some incoming objects are deflected away from the inner solar system, others are redirected into it. Its role is not simple and cannot be reduced to one function. What is clear is that Jupiter changes trajectories across a very broad zone. Around it lies a powerful magnetosphere, a magnetic environment so large that on some days it would appear wider than the full moon from Earth if it were visible. Charged particles trapped there create intense radiation, especially dangerous for spacecraft and for the surfaces of some moons. Jupiter's moons form a system of their own. There are dozens, ranging from small irregular captured bodies to major worlds. The 4 large Galilean moons are especially important. Io is heated by tidal forces and is the most volcanically active known world in the solar system. Europa has an icy shell and strong evidence for a global ocean beneath. Ganymede is the largest moon in the solar system and has its own magnetic field. Callisto preserves an ancient, heavily cratered surface. Each of these moons could be the main subject of a planetary story on its own. Yet here they remain within Jupiter's greater domain, circling a planet so massive that its moon system resembles a small secondary solar arrangement. Saturn, farther out at about 9.5 astronomical units, is less massive than Jupiter but still immense. Its atmosphere, like Jupiter's, is made mostly of hydrogen and helium. The planet is known most readily by its ring system, which is bright, broad, and structured in exquisite detail. The rings are made mostly of water ice particles with smaller amounts of darker material, ranging in size from fine grains to large chunks. Though they look solid from afar, they are composed of countless separate pieces orbiting Saturn. Gaps, waves, and narrow ringlets are shaped by gravity, including the influence of small moons that act as shepherds. The rings are extremely wide compared with their thickness. They form one of the flattest known large structures in the solar system. Saturn's moon system is also rich and varied. Titan, its largest moon, has a dense nitrogen atmosphere, lakes and seas of liquid methane and ethane, and a complex cycle of evaporation and rainfall under deep cold conditions. Enceladus is much smaller, yet it ejects plumes of water-rich material from fractures near its south polar region. indicating a subsurface ocean. Many other moons show cratered surfaces, mixed ice and rock, or unusual shapes and orbital histories. Saturn, like Jupiter, is not just a planet. It is the center of a system of worlds. To pass through its region is to pass through multiple scales at once, from planetary bulk to ring particles to moons with internal oceans. Farther still lie Uranus and Neptune, the ice giants. Uranus orbits at about 19 astronomical units. Neptune orbits at about 30. Both are smaller than Jupiter and Saturn, but much larger than Earth. Their atmospheres contain hydrogen and helium, above deeper layers richer in water, ammonia, and methane. Methane helps give both planets their blue color by absorbing red light. Uranus is especially notable for its extreme axial tilt, about 98 degrees, which makes it appear to rotate on its side. This likely results from a major impact or sequence of impacts early in its history, though the exact explanation remains uncertain. Because of this tilt, Uranus experiences unusual seasons over its long year, with poles spending decades in prolonged sunlight or darkness. Neptune, though smaller than Uranus in diameter, is more massive and denser. It is dynamic, with strong winds and storms despite receiving very little solar energy compared with Earth. The source of this activity is linked to internal heat, though details of atmospheric circulation continue to be studied. Neptune also exerts strong influence on the outer solar system. Its migration in early history likely helped sculpt the Kuiper belt and establish resonant populations such as Pluto's. Its large moon, Triton, is especially striking because it orbits in the opposite direction from Neptune's rotation, suggesting capture. Triton is cold, geologically interesting, and likely once formed elsewhere before becoming part of Neptune's system. All four giant planets possess rings, magnetic fields, and many moons. All create local systems that would be astonishing if viewed alone. Yet in the solar system they stand together as one broad region, separated by billions of kilometers of space. A traveller crossing from Jupiter to Neptune would still move through long emptiness between islands of complexity. The planets are huge, but the distances between them are larger still. Even these dominant worlds do not fill the outer solar system. They punctuate it. At this scale, Earth has become deeply interior and almost irrelevant to local structure. The giant planets contain most of the planetary mass in the solar system. Their gravity helps define the architecture of smaller bodies from asteroids to comets. Their moons include worlds with volcanoes, subsurface oceans, thick atmospheres, and active chemistry. The human home planet is smaller than all of them and less influential in the solar system's gravitational design. The unsettling measure grows clearer. What appears immense on Earth becomes ordinary beside a giant planet, and what appears dominant among planets still occupies only isolated stations in an outer realm where darkness, distance, and cold remain the prevailing condition. Between the region of the giant planets and the inner rocky worlds lies the asteroid belt, a broad zone of small bodies orbiting the Sun mainly between Mars and Jupiter. In older imagination, this region is sometimes pictured as a crowded hazard of tumbling rocks pressed close together. The reality is quieter and much more empty. The asteroid belt contains many objects, from dust grains to dwarf planet-scale bodies, but the distances between substantial asteroids are usually vast. A spacecraft can cross the belt without weaving through dense debris. The belt is a population, not a wall. It is a region where countless remnants of early solar system formation continue to orbit, shaped by collisions, sunlight, and above all by gravity, especially the gravity of Jupiter, The belt lies roughly between 2 and 3.5 astronomical units from the Sun. Within this broad corridor, bodies circle in the same general direction as the planets, mostly near the plane of the solar system, though with a range of eccentricities and inclinations. An eccentric orbit is one that departs from a near-perfect circle. Some asteroids follow fairly regular paths, others have more tilted or elongated orbits. The belt is not uniform. It has zones of higher and lower population, families of fragments from ancient collisions, and gaps where orbital resonances with Jupiter make long-term stability difficult. These are called Kirkwood gaps, and they are one of the clearest signs that the asteroid belt is not merely a leftover pile of matter, but a dynamically shaped region under continuing gravitational influence. The total mass of the asteroid belt is much smaller than that of a planet. In fact, all the material in the belt added together would still amount to only a small fraction of Earth's mass. This matters because it corrects a common impression. The asteroid belt is not the shattered remains of a large planet that once existed there. Observations and models indicate instead that the material in this region never assembled into a major planet in the first place. Jupiter's gravity, acting from nearby, stirs the orbits of growing bodies and raises their collision speeds. When collisions become too fast, objects are more likely to break apart than merge gently. In this way, the presence of Jupiter helps prevent planet formation from proceeding fully in this zone. The belt remains a record of interrupted assembly. Composition varies across the belt. Many asteroids in the inner belt are relatively richer in silicate rock and metal. Farther outward, darker carbon-rich bodies become more common, and in the outer parts, some asteroids contain more water-bearing minerals or ice-related material. These broad patterns reflect temperature differences in the early solar system. Closer to the Sun, only more heat-resistant materials remain solid. Farther out, cooler conditions allow different compounds to survive. Though later mixing and collisions complicate the picture, the belt still preserves traces of the ancient thermal gradient in the disk from which the planets form. The largest object in the asteroid belt is Ceres. Ceres is large enough for gravity to pull it into a nearly round shape, which places it in the category of dwarf planet. It contains a substantial fraction of the belt's total mass by itself. Observations from the Dawn spacecraft reveal a world with salts, water-rich minerals, impact features, and signs that briny material once moves or rises beneath the surface. Ceres is not simply a large rock. It is a small planetary body with a history of internal change. Yet even Ceres is modest in size compared with Earth's moon. Its importance comes less from bulk than from what it preserves about the early solar system and the presence of water-related materials in this region. Other large asteroids include Vesta, Pallas, and Hygiea. Vesta is especially notable because it appears differentiated, meaning it once becomes hot enough for denser materials to sink inward and lighter materials to rise, producing an internal structure more like that of a small terrestrial planet. Its surface shows enormous impact basins, and meteorites found on Earth have been linked to Vesta by their chemistry and by spectral observations. Pallas has an unusual tilted orbit. Hygiea, dark and carbon-rich, may also approach roundness. Around these larger bodies orbit countless smaller asteroids, many of them fragments from collisions that shatter parent objects over billions of years. Collisions are central to the belt story. Although the belt is sparse, time is immense. Over the age of the solar system, even infrequent impacts accumulate into a long history of breakage and resurfacing. Some asteroid families are groups of objects that share similar orbits and appear to be fragments of a common parent body destroyed in a major collision. Others are rubble piles, loose collections of broken material held together by gravity rather than solid monolithic rock. Spacecraft visits to asteroids such as Itokawa, Bennu, and Ryugu, though not all main belt objects, show that many small bodies are not single intact stones, but delicate aggregates with complex surfaces, boulders, and regolith. Regolith is the layer of loose broken material covering a solid body. This insight helps explain how asteroids respond to impacts, sunlight, and tidal forces. Sunlight itself can slowly alter asteroid motion. When an asteroid absorbs sunlight and later re-radiates energy as heat, the timing and direction of that thermal emission can produce a tiny force. Over long periods, this effect can shift an asteroid's orbit. This process is known as the Yarkovsky effect. It is very small moment by moment, but over millions of years it can move bodies into resonances that then change their paths more dramatically. Some asteroids are nudged out of the main belt and become near-Earth asteroids, crossing the orbits of the inner planets. In this sense, the asteroid belt is not perfectly sealed from the rest of the solar system. It slowly leaks material inward. Meteorites that land on Earth often come from this region. They are fragments of asteroids, delivered by collisions and orbital changes. Through them, laboratories on Earth can study material older than any rock formed on Earth's active surface. Some meteorites preserve tiny grains that predate the solar system itself. Others record melting, shock, or aqueous alteration on their parent bodies. The asteroid belt therefore acts as an archive. It stores material from the early solar system in bodies too small to erase their beginnings completely, yet large enough to preserve a long geological memory. At this scale, the belt appears less like a dramatic obstacle, and more like a quiet boundary zone. It separates the giant planets from the inner terrestrial planets, but it does not divide them with a solid barrier. It marks a transition in composition, in temperature history, and in gravitational influence. It is a place where planet formation nearly succeeds but does not finish, where bodies remain numerous yet individually small, where the leftovers of cosmic construction continue to circle under the distant control of Jupiter and the steady light of the Sun. The human world lies well inside this corridor, but even here, in one of the solar system's intermediate regions, the lesson remains the same. Earth is surrounded not by neat simplicity, but by layers of ancient structure extending outward and inward, each one larger and older than ordinary life can easily comprehend. Inside the asteroid belt, the solar system becomes warmer, more compact, and more familiar in composition. This is the region of the inner planets Mercury, Venus, Earth, and Mars. These are the terrestrial planets, meaning worlds made chiefly of rock and metal with solid surfaces. They differ from the giant planets not only in size, but in structure, density, atmosphere, and origin. In the inner solar system, sunlight is stronger, orbital periods are shorter, and volatile substances such as water, methane, and ammonia are less able to remain stable in exposed surface conditions during the early stages of formation. The worlds that emerge here are smaller than the giants, yet denser and more physically compact. They occupy only a narrow band of distance compared with the huge spread of the outer system. Mercury lies closest to the Sun, at an average distance of less than half an astronomical unit. It is the smallest of the 4 inner planets and the one with the shortest year. Its surface is heavily cratered, preserving the record of ancient impacts. Mercury has a large, iron-rich core relative to its size, which gives it a high average density. It possesses a very thin exosphere rather than a substantial atmosphere. An exosphere is an extremely tenuous outer layer of atoms and particles that do not behave like a dense blanket of air. Because Mercury lacks a thick atmosphere to trap heat or redistribute it effectively. Surface temperatures vary greatly between day and night. Near the Sun, it might seem natural to imagine constant heat everywhere, but the absence of atmospheric insulation produces extremes instead of uniform warmth. Venus comes next, similar to Earth in size but profoundly different in surface conditions. It is wrapped in a dense atmosphere composed mostly of carbon dioxide, with clouds of sulfuric acid high above the surface. This atmosphere produces a strong greenhouse effect. A greenhouse effect occurs when a planet's atmosphere allows sunlight to enter but slows the escape of heat back to space. On Venus, this process has produced surface temperatures hot enough to melt lead. The pressure at the surface is crushing, about 90 times that at sea level on Earth. Radar mapping reveals mountains, plains, volcanic features, and signs of geological resurfacing. Venus rotates slowly and in the opposite direction to most planets, a pattern called retrograde rotation. The exact cause of this unusual spin remains uncertain, though major impacts and later atmospheric effects are both considered important possibilities. Earth, third from the Sun, occupies a middle thermal zone where liquid water can persist at the surface under present conditions. Its composition includes a metallic core, a rocky mantle, and a crust, along with oceans and an atmosphere rich in nitrogen and oxygen. Earth is not the largest terrestrial planet by much, but it is the densest in the solar system. Its active geology is shaped by plate tectonics, the movement of large crustal plates across the surface. Its atmosphere moderates temperature, supports weather, and protects the surface from much harmful radiation. The Moon, unusually large relative to Earth, strongly affects tides and helps stabilize Earth's axial tilt over long periods. In the context of the inner planets, Earth appears distinctive because of surface water and life, but is still fundamentally one rocky planet among four. Mars lies beyond Earth, smaller, colder, and more thinly wrapped in atmosphere. Its air is composed mostly of carbon dioxide, but the atmosphere is too thin to maintain warm surface conditions across most of the planet today. Mars shows enormous volcanoes, deep canyons, polar ice caps, ancient river valleys, sedimentary layers, and minerals that form in water. These features indicate that liquid water once flows more widely at the surface or near it, especially early in Martian history. Much of that ancient habitability has been lost as Mars cools, its magnetic field weakens, and much of its atmosphere escapes or is otherwise reduced. Even so, water ice remains abundant, especially in the polar regions and underground. And modern Mars is still an active subject of study because it records a transition from a wetter early world to a colder, drier present one. The inner planets share some broad traits. All are made largely of rock and metal. All have experienced bombardment by smaller bodies. All likely form through accretion, a process in which smaller solid bodies collide and merge to build larger ones. In the young solar system, dust grains stick together, forming larger aggregates, then planetesimals, and later planetary embryos. A planetesimal is a small early building block of planets. Through repeated collisions and gravitational interactions, the terrestrial planets emerge. Their growth is violent, impacts release heat, and radioactive decay inside young planets adds more. Heavier materials sink inward, creating cores, while lighter silicates rise outward. This differentiation helps establish the internal layering seen in the rocky planets. Yet the inner planets also diverge sharply over time. Mercury remains small and bare. Venus becomes an extreme greenhouse world. Earth maintains long-lived oceans and active tectonics. Mars loses much of its atmosphere and cools into a more geologically subdued planet. Though not a wholly dead one, these differences arise from size, distance from the Sun, atmospheric history, magnetic protection, volcanic outgassing, and chance events such as major impacts. Small changes in starting conditions can lead to very different planetary outcomes over billions of years. The spacing of the inner planets is narrow compared with the outer system. Mercury, Venus, Earth, and Mars all fit within a distance from the Sun smaller than Jupiter's orbit alone. This compactness matters for any sense of scale. The region containing the worlds most similar to Earth occupies only a thin inner fraction of the solar system. Beyond Mars lies the asteroid belt, then the giant planets, then the Kuiper belt, then the vast inferred sphere of the Oort cloud. The rocky worlds where a human mind might most readily imagine standing are confined to a small inner strip close to the star. Sunlight in this region is strong enough to dominate surface conditions directly. On Mercury it scorches the day side. On Venus it drives an atmosphere that traps heat almost beyond moderation. On Earth it powers climate, weather, and photosynthesis. On Mars it is weaker, yet still sufficient to shape seasons, winds, and the motion of dust. The inner planets are the solar system's sunlit stones, close enough for radiation to matter at the surface every day, yet different enough from one another that no single rocky planet can be taken as typical. At this scale, Earth begins to feel nearer in the narrative, but its special familiarity remains deceptive. It is not the centre of the inner region, not the largest rocky world by an overwhelming margin, and not the only planet with atmosphere, weather, volcanoes, or water in some form. It is one outcome among several. The unsettling fact is not that Earth is unimportant in every sense, but that even within the narrow inner planetary band, it is one member of a small class shaped by physical rules far larger than itself. The region where solid ground exists under open sky is only a thin ring around one ordinary star. At the scale of Earth in orbital context, the solar system narrows from a region of several planets to one world moving through space under the constant pull of the Sun and the nearby influence of the Moon. Earth is not fixed in a quiet position. It travels around the Sun at an average distance of 1 astronomical unit, rotating on its axis while orbiting along a path that takes 1 year to complete. The Moon circles Earth while both bodies together continue around the Sun. This motion places Earth within a local environment of radiation, particles, gravity, and debris that extends beyond the planet's surface and atmosphere. Before reaching oceans, land, and life, it is necessary to remain in this surrounding orbital region, where Earth exists as a moving planetary body rather than as a lived landscape. Earth's orbit is slightly elliptical rather than perfectly circular, though the difference is modest. This means the planet is sometimes a little closer to the Sun, and sometimes a little farther away during the year. The changing seasons, however, are caused mainly not by this distance change but by Earth's axial tilt. The axis is tilted by about 23.5 degrees relative to the plane of Earth's orbit. Because of this tilt, each hemisphere receives changing angles and durations of sunlight during the year. The tilt does not make one hemisphere permanently warmer than the other. Instead, it produces alternating seasons as Earth moves around the Sun. In orbital context, climate begins not with air and ocean, but with geometry. The Earth-Moon system is unusual among the inner planets because the Moon is large relative to Earth's size. The leading explanation is that the Moon forms after a giant impact early in Earth's history, when a Mars-sized body collides with the young Earth and ejects material into orbit. That material later gathers into the Moon. Some details of this process remain under study, especially the exact conditions of the impact and the mixing of material, but the giant impact framework is strongly supported by chemistry, angular momentum, and modelling. The result is a paired system in which Earth and Moon orbit a shared centre of mass located inside Earth, but not exactly at its centre. The Moon's presence matters deeply even at this outer regional scale. Its gravity raises tides in Earth's oceans and also produces smaller deformations in the solid planet. Tidal friction gradually slows Earth's rotation and causes the Moon to drift slowly farther away over time. In the distant past, Earth's day is shorter and the Moon is closer. Over immense spans, the rhythm of the Earth-Moon system changes. The Moon also contributes to the long-term stability of Earth's axial tilt. Without a large Moon, the tilt of a planet can vary more chaotically under gravitational influence from other bodies. Earth's climate history is still complex, but the Moon helps reduce one potential source of large instability. Beyond the Moon's orbit, Earth moves through a stream of energy and particles coming from the Sun. Sunlight provides the dominant incoming energy, but the Sun also emits the solar wind, a flow of charged particles moving outward through the solar system. Earth's magnetic field interacts with this flow and creates the magnetosphere, a large magnetic cavity surrounding the planet. The magnetosphere deflects many charged particles and channels some toward the polar regions, where they can produce auroras. This magnetic shield does not block all radiation, and its shape changes under solar conditions. On the side facing the Sun it is compressed. On the night side it stretches into a long magnetic tail extending far into space. Earth in orbit is therefore not simply a sphere in light. It is a planet with an electromagnetic envelope moving inside the Sun's outflow. Within this near-Earth region lie belts of charged particles trapped by the magnetic field, known as the Van Allen radiation belts. These zones contain energetic electrons and protons. Their intensity varies with solar activity and with geomagnetic conditions. They are important for satellites, spacecraft electronics, and human spaceflight because prolonged exposure can damage materials and living tissue. The existence of these belts is another reminder that the region around Earth is physically active. Empty space near the planet is not truly empty. It contains radiation, plasma, micrometeoroids, and artificial objects placed there by human technology. Earth also shares its orbital neighborhood with small natural bodies. Meteoroids cross near its path. Some are tiny grains shed by comets. Others are fragments from asteroids. When they enter the atmosphere, they produce meteors, and if a portion reaches the ground, it becomes a meteorite. Most are small and burn up high above the surface, but larger impacts have occurred many times in Earth's history. Craters on the Moon and other bodies show how common impacts are in solar system history. While Earth's active geology and weather erase many older traces, even in its present orbital setting, Earth remains vulnerable to incoming debris. Surveys track many near-Earth asteroids, yet not every small body is known. Observations have improved greatly, but the catalogue is never absolute. Artificial satellites now occupy parts of Earth's orbital environment as well. They circle at many altitudes, serving communication, navigation, weather monitoring, science, and military functions. Some orbit low and move quickly across the sky. Others remain far higher, matching Earth's rotation closely enough to stay above nearly the same region of the equator. Around them is a growing population of spent rocket stages, fragments, and debris. This layer of human-made material is tiny compared with the solar system, but it is significant in near-Earth space because orbital speeds are high and collisions can create more fragments. The orbital region immediately around Earth has therefore become not only a natural environment, but also a technological one. From farther away, Earth is a small reflective planet with a thin atmosphere, white cloud systems, polar ice, dark ocean basins, and changing land patterns. It shines by reflected sunlight. Its total extent is tiny compared with the distance to the Moon, and microscopic compared with the size of its orbit around the Sun. The orbit itself is tiny compared with the full solar system. Yet this small moving world carries all known life. That fact can seem to enlarge Earth in importance, but it does not enlarge it in physical scale. Physically, Earth remains one small rocky planet in one orbit, embedded in a system governed chiefly by the Sun and secondarily by countless interactions among matter, light, and gravity. At this scale, the familiar world is still not yet the ground beneath feet. It is a sphere suspended in motion, accompanied by a moon, wrapped in magnetic structure, crossed by particles and debris, and carried around a star through a broad gravitational field. Mountains, oceans, forests, and cities do not yet appear. Earth first exists here as a planet among orbital processes. The unsettling proportion remains unchanged. All human history occurs not only on a small world, but on a small world that itself occupies a narrow path around an ordinary star, surrounded by layers of space that operate with complete indifference to the brief lives unfolding below. Earth's atmosphere and surface form the next inward region, the outer physical layers of the human world. From orbit, the atmosphere appears as a thin luminous shell around a rocky sphere partly covered by water. This thinness is one of the most important facts about Earth. Compared with the planet's full size, the breathable lower atmosphere is a very shallow layer. Almost all weather clouds and ordinary life processes occur within only a small fraction of Earth's radius. Beneath that layer lies the surface itself, divided between ocean basins and continents, shaped by internal heat, sunlight, gravity, water, ice, and air. At this scale, Earth becomes the first place in the narrative where a human body could stand. Yet even here the habitable region remains strikingly narrow. The atmosphere is composed mainly of nitrogen and oxygen, with smaller amounts of argon, carbon dioxide, water vapor, and trace gases. Though the mixture is simple in broad terms, its behavior is dynamic. The lowest layer is the troposphere, where most clouds form and most weather takes place. Temperature generally decreases with height in this layer because the troposphere is heated from below by Earth's surface, which absorbs sunlight and re-radiates energy upward. Above it lies the stratosphere, where temperature rises with height because ozone absorbs ultraviolet radiation from the sun. Higher still are the mesosphere, thermosphere, and exosphere, where the air becomes progressively thinner and conditions shift away from ordinary weather into chemistry, radiation, and particle interactions. These upper regions matter greatly for shielding and energy balance, but they are too thin for breathing and too harsh for unprotected life. The atmosphere performs several linked functions. It carries heat from one region to another through winds and circulation cells. It holds water vapor, allowing clouds, rain, snow, and storms. It scatters sunlight, making the daytime sky appear blue and the horizon bright. It slows heat loss at night and moderates temperature differences between day and night, especially where moisture and clouds are abundant. It also filters harmful solar radiation. Ozone in the stratosphere absorbs much ultraviolet light that would otherwise damage living tissue more severely. Without an atmosphere, Earth's surface would be a much harsher place, with stronger radiation exposure, more extreme temperature swings, and no ordinary weather or rainfall. Water shapes the surface as strongly as air does. About 7/10 of Earth's surface is covered by oceans. This means the dominant visible feature of the planet from space is not land but water. The oceans store heat, transport it through currents, dissolve gases, shape climate, erode coastlines, and sustain a large share of Earth's biosphere. Their average depth is much smaller than Earth's radius, yet their effect on the planet is enormous. Ocean water cycles into the atmosphere by evaporation, returns by precipitation, and flows across land through rivers and groundwater before reaching the sea again. This hydrologic cycle links sky, surface, and subsurface into one continuous exchange. The continents rise above sea level as thicker, less dense sections of the outer rocky shell. Their arrangement is not fixed. Earth's crust is broken into tectonic plates that move slowly across the planet's surface over millions of years. This process is called plate tectonics. New crust forms at mid-ocean ridges where plates separate. Old crust descends back into the mantle at subduction zones where plates converge. Mountain ranges rise where plates collide. Earthquakes occur as stress is released along plate boundaries and faults. Volcanoes form where molten rock reaches the surface, especially above subduction zones, at rifts, and at some hotspots. The surface, therefore, changes continuously, though usually too slowly for ordinary human perception, except during sudden events such as eruptions or earthquakes. This moving crust gives Earth a surface unlike that of Mercury, the Moon, or Mars, where ancient craters often remain for immense spans. On Earth, erosion, sedimentation, tectonic recycling, and plant activity erase or bury many old features. Rain, rivers, ice, wind, and waves wear rock down and move it elsewhere. Sediment gathers in basins, hardens into stone, and may later be lifted into mountains. Glaciers carve valleys, deserts shift dunes, coasts retreat or advance. Even where the solid ground seems permanent, change is constant. The apparent stability of a landscape usually depends on the shortness of the human lifetime, not on true stillness. Climate emerges from the combined action of sunlight, atmosphere, oceans, ice, landforms, and planetary rotation. The equator receives more direct sunlight on average than the poles, creating a basic temperature gradient. Earth's rotation helps organize winds into large circulation patterns and influences ocean currents through the Coriolis effect. The apparent deflection of moving air and water caused by rotation. Mountains redirect winds and force air upward, producing rain on one side and dryness on the other. Ice and snow reflect more sunlight than dark ocean or forest, creating feedbacks that influence temperature. Clouds both cool and warm, depending on altitude, thickness, and time of day. Climate is therefore not one single mechanism, but the integrated behavior of many connected systems. Earth's surface also includes the cryosphere, the realm of frozen water in glaciers, ice sheets, sea ice, snow cover, and permafrost. Though limited in area compared with the oceans, ice has strong effects on sea level, ocean circulation, and planetary reflectivity. Large ice sheets on Greenland and Antarctica hold most of Earth's fresh water in frozen form. Their growth and retreat over geological time alter coastlines and climates far from the poles. Frozen water also shapes mountains, soils, and ecosystems through melt cycles and long-term storage. In this way, even the coldest surface regions participate in the same planetary exchange that connects atmosphere, ocean, and rock. At the human scale, mountains seem vast, storms seem powerful, and oceans seem without end. At the planetary scale, all of these are surface phenomena operating in thin layers. The highest mountains rise only a small distance compared with the Earth's diameter. The deepest ocean trenches cut only slightly into the outer shell. Hurricanes, jet streams, and thunderclouds fill a shallow atmospheric envelope. Even the continents are skin-deep compared with the planet's full interior. Earth's active surface, for all its drama, is a delicate film on a much larger sphere. This is the quiet truth of the atmosphere and surface. The region that feels complete to human life is physically slight. Air, water, coastlines, forests, deserts, storms, and mountain chains all exist in a narrow zone where sunlight, gravity, and chemistry briefly cooperate. Everything familiar unfolds in layers so thin that from a sufficient distance they nearly vanish. Earth does not offer a broad platform of comfort suspended in space. It offers a very small margin where conditions happen to remain workable, wrapped around a planet that is itself small within the solar system and minute within the galaxy. The world of weather and stone feels expansive from within it, but in physical proportion it is scarcely more than a skin. Inside the atmosphere and across the surface lies an even thinner region, the biosphere. The biosphere is the part of Earth where life exists, including living organisms and the environments that sustain them. It is not the whole planet. It is a narrow band that extends from the deepest inhabited ocean waters into the lower atmosphere. But the vast majority of its activity occurs close to the surface. Compared with Earth's radius, the biosphere is extremely thin. Compared with the scale of the solar system, it is negligible. Yet it is the only region known to contain life, and it holds the processes that transform air, water, and rock into a living system. Life exists in the ocean from the sunlit surface down to deep seafloor habitats where light never reaches. In the upper ocean, photosynthetic organisms capture sunlight and convert it into chemical energy. Photosynthesis is the process by which some organisms use light to build organic molecules from carbon dioxide and water, releasing oxygen as a byproduct. In the ocean, much of this work is done by microscopic algae and cyanobacteria drifting near the surface. These organisms form the base of marine food webs and produce a large share of Earth's oxygen over long time. Beneath them, in darker waters, life continues by feeding on organic particles that sink from above or by exploiting chemical energy from the seafloor. In the deepest ocean, hydrothermal vents and cold seeps support communities that rely on chemosynthesis. Chemosynthesis is the process by which organisms build organic molecules using chemical energy rather than sunlight. At vents, hot mineral-rich water emerges from the seafloor, providing hydrogen sulfide and other compounds that microbes can use as energy sources. These microbes support larger organisms such as tube worms, clams, and crustaceans. Such ecosystems show that life can persist without direct sunlight as long as energy and usable chemistry are present. Yet even these deep systems remain part of the biosphere's narrow zone. They exist on the skin of the planet, not in its deep interior. On land, life occupies soils, forests, grasslands, deserts, wetlands, and polar regions. Plants anchor many terrestrial ecosystems by capturing sunlight and building biomass. Their roots break rock into soil, stabilize sediment, and alter water flow. Microbes in soil decompose organic matter, cycling nutrients back into forms that plants and other organisms can use. Fungi link roots through networks that move water and minerals. Insects pollinate flowers and recycle material. Larger animals redistribute nutrients and seeds. Each of these processes depends on the thin layer of atmosphere that supplies oxygen and carbon dioxide, the water that moves through ground and air, and the moderate temperatures that allow liquid water to remain stable for much of the year. The biosphere extends upward into the lower atmosphere as well. Microbes and pollen can be carried by winds. Birds and insects move through air. The chemistry of the atmosphere itself is influenced by life. Oxygen in large amounts is a biological product over geological time, maintained by photosynthesis and balanced by processes that consume oxygen such as respiration, decay, and oxidation of rocks. Methane is produced by some microbes and by human activity. Nitrous oxide arises from biological processes in soils and oceans. Even water vapor is strongly linked to life through transpiration, the release of water from plant leaves. The air is therefore not merely a physical layer above life, it is partly shaped by life. Despite its power to transform Earth, the biosphere is fragile in physical extent. Most life occupies a zone measured in kilometers, not thousands of kilometers. Even the highest mountain ecosystems exist only a small distance above sea level compared with Earth's radius. The deepest inhabited marine trenches are still only a small distance below the surface. The total thickness of the biosphere is small compared with the depth of Earth's mantle and core. Life does not fill the planet. It clings to a narrow interface where energy flows and chemistry remains workable. Energy is one of the simplest constraints on this thinness. Almost all energy available to the biosphere ultimately comes from the sun. Sunlight is strongest near the equator and weaker toward the poles. It is filtered through the atmosphere and reduced by clouds, dust, and seasonal angles. In the ocean, light penetrates only the upper layers before being absorbed. This creates a photic zone, the region where light is sufficient for photosynthesis. Below that zone, life must depend on chemical energy or on material drifting down from above. On land, sunlight drives plants, and plant growth drives much of the animal life that follows. When energy is limited, the density and diversity of life often decline, though life can still persist. Water is another constraint. Life as known on Earth depends on liquid water. This requirement immediately confines most activity to regions where water is present in usable form. Deserts show that even under sunlight, life is limited where water is scarce. Polar regions show that life is limited where water is locked in ice much of the time. Oceans show that water alone is not sufficient if nutrients are scarce or if light is absent. The biosphere therefore occupies not just the wet parts of the planet, but the parts where water, energy, and nutrients intersect. Nutrients circulate through the biosphere in cycles. Carbon moves through atmosphere, ocean, rock, and living tissue. Nitrogen moves through air, soil, organisms, and water, with microbes playing a central role in converting nitrogen into forms plants can use. Phosphorus moves mainly through rock, soil, and water, often limiting biological productivity because it is less abundant and less mobile than carbon or nitrogen. These cycles depend on the surface environment. They're driven by sunlight and by geological processes such as weathering, volcanism, and tectonic uplift that expose fresh minerals. Life both uses these cycles and modifies them. The biosphere is therefore a dynamic system woven into the planet's surface physics and chemistry. The biosphere also has a deep time history. For billions of years, life alters Earth's atmosphere and surface, leaving evidence in fossils, sediments, isotopic signatures, and rock chemistry. Mass extinctions occur, wiping out many species, yet life persists and diversifies again. The present richness of life is a moment in this long sequence, shaped by ancient events and by ongoing ecological interactions. This history does not expand the physical size of the biosphere. It only shows how much transformation can occur within a thin layer. At this inward region, the measure of smallness becomes almost physical in the mind. The habitable world is not a thick globe of living matter. It is a film. It is connected but slender zones stretched over ocean and land, rising only a little into the air and sinking only a little into the sea. Everything that breathes, grows, moves, and reproduces exists within this narrow range. The planet beneath is largely lifeless rock, mantle, and core. The space above becomes quickly too thin and harsh. The universe outside remains indifferent. Life occupies a boundary surface of extraordinary complexity and productivity, yet its physical dimensions are slight. The chilling truth here is not that life is meaningless, but that it exists on a margin so thin that from a wider scale it nearly disappears. Within the biosphere, the scale narrows once more to the human body, a temporary arrangement of matter organized by biology and sustained by flows of energy, air, water, and nutrients. At this innermost inhabited level, the comparison with the universe becomes most intimate and most stark. A human being is not merely small in a poetic sense. A human being is physically minute relative to the planet, microscopic relative to the solar system, and effectively absent at galactic scale. Yet the body is built from the same kinds of matter found throughout the cosmos. Hydrogen, oxygen, carbon, nitrogen, calcium, iron, phosphorus, sulfur, sodium, potassium, and trace elements are assembled into cells, tissues, organs, and systems. The human form is therefore both cosmically connected and cosmically tiny. The body begins as a multicellular structure, meaning it is composed of many cells working together. A cell is the basic living unit enclosed by a membrane, containing molecular machinery that uses energy, handles information, and maintains internal conditions. The human body contains tens of trillions of cells, though exact totals vary with age, sex, body size, and method of estimation. These cells are not all alike. Muscle cells contract, nerve cells conduct signals, blood cells transport gases or support immunity, skin cells form barriers, bone cells maintain mineralized tissue. Each cell is small beyond unaided sight, yet large compared with many molecules and atoms. Life operates by organizing matter across layers of scale, each one nested inside the next. Inside cells or organelles and molecular systems, proteins fold into shapes that determine what they do. Lipids form membranes. Carbohydrates store and provide energy or structural support. DNA carries hereditary information through sequences of chemical bases. A molecule is a group of atoms bound together, and in living tissue these molecules form dynamic networks rather than static pieces. Water surrounds them, transports dissolved substances, and supports the chemistry of life. Much of the body by molecule count is water. Much of its mass is oxygen, carbon, hydrogen, and nitrogen. These are common cosmic elements, formed through the history of stars and the early universe. The body feels personal and singular, yet in material terms it is made from ordinary ingredients. atoms are the next inward level. An atom is the basic unit of a chemical element, composed of a nucleus of protons and neutrons surrounded by electrons. The nucleus is tiny compared with the full size of the atom. Most atomic volume is empty space, in the sense that matter is not packed continuously through it. Electrons occupy quantum states, described by probabilities rather than little planetary orbits in the old picture. But the practical result remains that ordinary solid matter is mostly structured emptiness at very small scales. When a hand rests on a table, the sensation of solidity comes not from continuous packed substance, but from electromagnetic interactions between atoms. Matter at human scale feels dense and firm. Matter at atomic scale is sparse and relational. Within the nucleus lie protons and neutrons, themselves built from quarks bound by gluons according to the strong interaction. These terms name the current standard model of particle physics, the framework that describes known fundamental particles and several of the forces acting between them. At this level, the language becomes more abstract because direct human experience offers no guide. Still, the broad point remains simple. The human body is not made of a special category of matter set apart from stars, rocks, or gas clouds. It is made of the same fundamental particles organized under local conditions into chemistry, cells, and consciousness. The difference is arrangement, not substance. Scale changes the meaning of significance. At the human level, a body fills space, moves with intention, senses, remembers, and acts. At the cellular level, the same body becomes a dense ecosystem of cooperating units. At the molecular level, it becomes a swarm of chemical reactions. At the atomic level, it becomes patterned emptiness with nuclei and electrons. At the subatomic level, familiar bodily identity vanishes into fields and interactions. None of these descriptions is false. Each is true at its own scale. Yet each one dissolves the ordinary impression that the human body is a stable central object in nature. It is a temporary structure maintained against decay by constant exchange with the environment. Breathing draws oxygen from the atmosphere and releases carbon dioxide. Eating transfers atoms from plants, animals, fungi, and microbes into living tissue. Drinking replaces water that is continually lost. Heat leaves the body into surrounding air, water, or surfaces. Cells die and are replaced. Molecules are broken down and rebuilt. Over time, much of the matter in a body is exchanged. The identity that feels fixed is carried less by permanent material than by organization and continuity of process. Even at the scale of one lifetime, the body is not a sealed object. It is an open system moving matter and energy through itself. Its persistence depends on the narrow habitable layer of Earth, which depends on the atmosphere, which depends on the planet, which depends on the sun, which depends on the galaxy, which depends on the broader universe. Size becomes more unsettling when measured outward from the body. A body is small compared with a house. A house is small compared with a city. A city is small compared with a continent. A continent is small compared with Earth. Earth is small compared with Jupiter, with the solar system, with the distance to nearby stars, with the Milky Way, with galaxy clusters, and with the cosmic web. This chain is not metaphorical. It is literal physical proportion. The body occupies a tiny span on a planetary surface, and that surface is a skin on a small world circling one ordinary star. Every ordinary act of walking, sleeping, eating, and looking at the sky occurs inside this compressed hierarchy of scale. Yet the body also contains an inward vastness of number. A single person contains trillions of cells and vastly more atoms. The smallness of human size does not mean simplicity. It means that complexity can be concentrated into a very limited volume. Biological order emerges within strict physical boundaries, using local gradients of energy and chemistry to hold itself together for a time. This makes the body both precious and physically modest. Its capacities do not enlarge its dimensions. Thought does not increase size. Awareness does not change proportion. A conscious being remains materially tiny. At the innermost inhabited scale, the full argument of proportion comes to rest. The human body is composed of common cosmic matter, arranged briefly into living form on a narrow habitable layer of a small planet, inside a thin inner ring of one solar system, inside one region of one galaxy, inside one web of matter in the observable universe. Nothing in that chain enlarges the body, it only locates it. The chilling truth is not that the body is unreal or insignificant in every possible sense. It is that physically, in measure and extent, it is almost nothing. It is a brief pattern of atoms able to notice the scale that contains it. The scale has now narrowed as far as it can while still remaining within the inhabited world. The journey begins with the widest visible structure, where galaxies trace a faint web across darkness, and it comes to rest in the living body, where atoms are arranged for a short time into thought and breath. Between those two limits, every familiar place becomes smaller. Clusters of galaxies become knots in a larger pattern. The Milky Way becomes one spiral among many. The solar system becomes a small domain around one star. Earth becomes a thin-skinned world with a narrow atmosphere. The biosphere becomes a film upon the surface. A human being becomes a temporary structure within that film. Nothing in this progression is hostile by itself. The universe does not need malice to make human scale feel slight. Size alone is enough. Distance alone is enough. The outer universe does not bend inward to acknowledge the small living forms on one planet. It simply extends. The inner structure of matter does not pause to preserve the appearance of solidity and permanence. It simply continues into smaller arrangements and deeper laws. In both directions, outward and inward, ordinary intuition fails long before reality ends. Yet there is a calm fact within that loss of scale. The human body is small, but it is made from the same material history as stars and planets. The air, water, stone, cells, and atoms all belong to one continuous physical world. The smallest inhabited scale and the largest observed scale are not separate creations. They are connected by matter, energy, time, and law. A person does not stand outside the universe and look in. A person is one minute event within it, composed of its common elements, living briefly in one of its rare workable layers. The truth remains cold in proportion, but steady in meaning. The universe is vast beyond comfort, and the inhabited margin is thin beyond expectation. Still, within that narrow margin, awareness appears. A tiny arrangement of atoms becomes able to notice the stars.